So we identified 10 carbon atoms in AZT. And in this question, we're going to classify them in how many hydrogen atoms are attached to each. So throughout organic 1 and 2, there's only 4 scenarios: CH3, CH2, CH, and carbon with no hydrogens. So since I'm using the iPad here, I'll do it in color. So I'll highlight the CH3 in red. Maybe I'll get the highlighter on. So CH3. Now wherever there's a CH3 in that molecule, I'm going to highlight it red. So how many CH3 groups are there? I heard a 2, I heard more 1s, there's 1. So it's right here. And from that, we can eliminate C as a response, right? So let's move on. CH2, we'll do that in blue. So we have 2 CH2 groups. So the first one's right here. And then the second one is in this ring right here. So we're looking at a 1 and 2, so I think we can eliminate choice D at this point. If we're looking down the second column. Then in green, we'll do CH3, or excuse me, CH. How many CH groups are there? So 4. 1, 2, 3, 4. And so where are we at now? We can eliminate A, right? And so the answer's got to be B. But we'll go ahead with yellow highlighter and do the carbons that have no hydrogens attached to them. So we have this one double bonded to oxygen, and then this other one double bonded to oxygen. So again, what we're drilling down through is we looked at the structure, we determined how carbon was communicated, we counted 10 carbons. We've now classified them according to this method using the attached hydrogens. The reason this is important is because when we start learning about reactions, you have to be able to predict where the reaction is going to occur in the molecule. And so when we learn about reagents, the reagents will act at specific locations, and this will help guide us in figuring that out. So now we'll look at classifying the carbon atoms based on bonds. So before we did carbons with 4 sigma bonds, and this question is asking you about carbons with 3 sigma bonds and 1 pi bond. So how many do you think there are? What? There's 4. So I'm just going to use a dot now instead of the highlighter. So there's 1, 2, 3, and 4. So this would be A. So we had 10 carbon atoms. Wednesday's lecture, we said 6 of them had 4 sigma bonds. Today we said there are 4 with 3 sigma bonds and 1 pi bond, so that's 10. Now the last scenario is carbon atoms that will have 2 sigma bonds and 2 pi bonds. And so again, that highlights the difference between, carbon being an element with its atomic orbitals, and then carbon being in this molecule being in different bonding patterns. So we said there were 2 CH2 groups. So CH2, we identified 2 of those. So there and there. So look at this word right here, methylene. Again, there's a lot of vocabulary words that you're probably not used to ever knowing or hearing before, but these are the ways that we're going to communicate about the structure. So there's 2 CH2 groups. They're called methylene. And the reason, we use these terms, when I say look at the methylene groups in the molecule, you sort of know where to put your eyeball. The question says, are those 2 groups identical? What is no? You nod your head or shake your head? I think I saw more horizontal movements. So no, they are not identical. And what is the reason? Anyone that said no, why are they not the same? Yes. Right. So the test of answering this question is, imagine that you are hiking in the woods and you're on a point in the path, and you're looking left, you're looking right. Are those paths the same or are they different? So that's what you're doing on the molecule. The carbon backbone, is your path. You look to the left, the right, does it look the same? And so when you're standing here, that looks different, right? You have OH and then you have this carbon. When you're standing there, you have a carbon bonded to that. You look to the right, you have a carbon bonded to a nitrogen and oxygen. So when you do that test, you say, okay, those are different, so those things have to be different. And I'm going to use this word quite a bit this semester called uniqueness. And the uniqueness of the carbon or the hydrogen is going to tell us, based on the molecular formula, how we can start proposing structures. Again, we're going to ask questions, one way, we're going to ask it the reverse way, we're going to ask it sideways, so that ultimately we're painting a picture of the exact structure. So there are four CH groups, and these are called methine. So a CH3 group is called methyl, CH2 is methylene, CH is methine. So I'll show these in green here. So there's 1, 2, 3, and then 4. So are those groups identical? I heard some no's. No, they are not identical. And again, when you're looking to the adjacent or neighboring atoms, they're all in different environments. So that's how we determine that the CH groups are not the same. And again, why is this important? We're going to talk about a principle called selectivity later on in the semester. So if you have 4 of the same thing, how do you react at only one of them specifically? If you wanted to make a derivative of AZT at a specific position, but the reagent can react at four of them the same, how do you figure out which one it's going to go after? But for now, really what we're just doing is learning the vocabulary, learning how to, interrogate these molecules, saying it's this class or this type of carbon, this hybridization. So moving on to the carbons with no hydrogens. Do these in yellow. So what do you think about those? Are they the same? So those are not the same. I'm holding too much stuff. So no hydrogens, no hydrogens, no hydrogens. We know that there are no hydrogens because we're showing 4 explicit bonds to it. And they're not the same because, again, if you stand there, that carbon's bonded to a methyl group, and that's bonded to a carbon with a double bond to an oxygen. That's bonded to a nitrogen, that's bonded to a carbon with that methyl group, and that one is bonded to 2 nitrogens. So there's the test of answering that question. Yes?
Are there any that will actually be the same?
So the question was, are there any that will actually be the same? And as we progress through next week, yes, there will be. Again, I'm showing you a pretty complicated molecule to begin the core sequence of organic 1 and 2. For the purpose of indicating to you that this is AZT. I bought it from a chemical company called Sigma Aldrich. So it's in a little brown vial, but it's a white solid. And so I'll show you some pictures of it in a couple minutes. But again, this substance, this white solid, is used as a prescription drug for people that have HIV or AIDS. So that indicates the importance of the class. But next week we're going to go back to the beginning. We're going to look at the fundamental principles of electron configuration in the periodic table. Then we're going to start building these molecules back up. So we'll start with 1 carbon, then 2, then 3. And in that process, you'll see about the uniqueness where you can have things that are the same. Any question? Questions? Yes. So the question was about what would make the groups the same. So in your response, you said bonds, and that's essentially what we're going to look at. To give you a preview of that process, really it's the word we're going to use is symmetry. So we're going to draw molecules out, and then we're going to see if there's symmetry to the molecule. So does the left and the right side look the same? Like if you're on that hiking path, does this look like that? If you take both routes, you sort of get to the same place. So we have carbon, we have hydrogen. Anything that is not carbon or hydrogen is called a heteroatom. So hetero means different. And what are they? So typically, moving across, I just remember CNOF from the periodic table. So we move to the right. We have NOF. So nitrogen, oxygen, fluorine. So those are heteroatoms. If you go down the periodic table, we have phosphorus, sulfur, chlorine. So anything that's not carbon or hydrogen is called a heteroatom. And our next question says, how many carbon atoms, so you're looking at the carbons, are bonded to heteroatoms? Heard some sevens. Let's go ahead and highlight those. I'll do it in red here. So that's bonded to how many different heteroatoms? So 3 different heteroatoms, 4 total bonds. So that's 1, 2, 3, 4, 5, 6, and 7. Now, what's the point of this question? When you're looking at a molecular formula, you're going to obviously have more carbons and hydrogens than these other elements. What the other elements do to the molecule is impart polarity. Because remember, we said oxygen is showing 2 bonds, right? So 2 bonds, that's 4 electrons. We have 4 unaccounted for, so those are lone pairs. A lone pair of electrons, that's electron density. And so what that does is it changes the polarity of the bond. And again, that's important for predicting reactivity. So we counted 5 nitrogen atoms. And again, the heteroatoms are explicitly shown as their abbreviation from the periodic table. So oxygen is O, nitrogen's N, fluorine's F, etc. So are all 5 nitrogen atoms different? So yes, the nitrogen atoms are all different because they're bonded to different things. And again, the point of that is you have 5 of them, they're all 5 different. They're in different functional groups based on their bonding patterns. So yes, they are different. What about the oxygens? There's 4 oxygens. Are those all different? So yes. And again, we determined that by looking at what the oxygen's bonded to. That one has an H and a carbon. That has carbon and carbon. That has a CO double bond, as does that. You might think, hey, those are the same type of oxygen. But then when you go out further, you see that the environment is different. So that, again, you're gonna be, when you start reading the textbook, hopefully, does everyone have access to the textbook now? So they should have released that code to you or whatever in Canvas. When you start reading it, again, you're gonna see a lot of new terms, and however you wanna do it, whatever your best learning style is. I know index cards are popular for making like reaction and vocabulary terms so that you know what we're talking about. So here's a new term, carbonyl. So remember I said with carbons attached hydrogens, there was methyl, methylene, methine. A carbon doubly bonded to an oxygen is called a carbonyl. So a carbonyl group. And again, that's part of the nomenclature or naming system when we're talking about functional groups. So here they are. That's a carbonyl group. and that's a carbonyl group. So those are not the same, again, based on their bonding patterns. So the two other oxygens, so in the ring and up here, they have sigma bonds. So one has a sigma bond to hydrogen with a sigma bond to carbon, and the other one is two sigma bonds to carbon. Are those oxygen atoms the same? So no, they're different as well. So this oxygen, that oxygen. And so where we're going with this, I think the last slide today when I talk about, functional group names, this oxygen up here is called an alcohol. The oxygen that's bonded to two carbons that's in the ring is called an ether. E-T-H-E-R, ether. So when I say the word alcohol, it has to have an OH group. When I say the word ether, it's got to have an oxygen that's singly bonded to two different carbons. And again, so as we're communicating in this course, there's layers of thinking about things. There's the word alcohol, but then what does that represent chemically? It's the OH group bonded to a carbon. So this question states there are 3 explicitly drawn lone pairs of electrons shown. So those are on those nitrogens. There's also implicit lone pairs that are not shown. And so we have 3 that are shown, and the question is asking how many total electron pairs are there? 3 plus something equals our answer. So really to sort of funnel you into the right answer, you're not considering hydrogen or carbon. So we're looking at the heteroatoms, nitrogen and oxygen. So let's start with the oxygens. We'll draw them in. So remember, oxygen, let me sort of back up a minute. So CNOF. Carbon has 4 bonds, nitrogen 3, oxygen 2, halogens 1. And so if we multiply that number by 2, we're trying to get to the octet, right? So 4 times 2 is 8. So I'm just going to write LP for lone pair. Carbon would have 0 lone pairs, right? So nitrogen would therefore have 1, oxygen 2, and then halogens 3. So that's what we're doing. So oxygen up here, there's 2 lone pairs. That gets us our octet. Then in the ring, the 2 carbonyl groups, the one at the top, the one to the bottom right. Now we've drawn those in. So, typically on the slides, you're not going to see them because when I draw this stuff in the program that I use, it's kind of a pain in the butt. But they're there because we have to always, realize there's an octet. The bottom 3 nitrogens, those are taken care of, so we have the 2 other nitrogens. So we saw from our little chart that each nitrogen gets 1 pair. So if we count that up, what do we get? So 10 plus 3, that's 13. So 13 lone pairs of electrons. And again, what that will ultimately help us realize is what is sort of the polarity of the molecule. So, not a lot of you come from the same high school. Many of you don't have the same preparation. You come from maybe different Gen Chem sections or transfer students, other institutions, that sort of thing. But if we look at this question with Roman numeral 1 and 2 at the specific carbon atoms, what do you think the shapes of those carbon atoms are based on the bonding patterns that are shown? I heard an A, I heard a C. So the Roman numeral 1 has 3 sigma bonds, 1 pi bond. 2 has 4 sigma bonds. The consequence of that is they're going to have different shapes. And again, that's going to get back to the orbitals involved. So C is going to be the correct answer for this. So why is that? Again, carbon is carbon, but they're different bonding patterns. Roman numeral 2 carbon has 4 sigma bonds. The shape is going to be tetrahedral, which turns out that maximizes getting the things as far away from one another as possible. Roman numeral 1 is trigonal planar. So the 3 atoms bonded to it are all in a plane. So when I say trigonal planar, tetrahedral, linear, does that jog your memory about sort of bond angles and things like that as well? So we'll start talking about that next week. The bond angle affects the shape of the molecule. You have a question? It's this carbon right here. This doesn't show it very well because the bonds are like these. It's not a good representation of it. You see 2 things, right? Those are the bonds. But the sigma bond will be in one plane, and then the double bond is going to be sort of above and below that. And is it more what? It is polarized. So again, we'll have more visual representations of that stuff in the future lectures. Yes?
Why are the oxygens with sigma and pi bond different from each other?
So these 2 that I'm holding. So that carbon atom, so these 2 groups that I'm holding, just the 2 elements of that bond, C and O, those are the same, right? But if you look at the carbon that I'm holding now, that carbon is bonded to a nitrogen, this one's bonded to a carbon. Now this one is bonded to 2 nitrogens. So because that carbon is different, those groups then have to be different. Any other questions before we soldier on? Yeah.
To follow back on that one, the path that we follow, we look at both ways. Okay.
So I'll tell you right now, I think a stumbling block for a lot of students is it's like, I want to know the answer. And organic chemistry really is not like that. you have to evaluate these routes, these paths. You do have to look right, you do have to look left and make those decisions. So don't get your blinders on and ignore like some other part of the molecule or whatever. Just make sure that you're sort of taking it all in before you commit to a response. Okay, to sum up what we've learned in the first 90 minutes of the semester here, these are the answers to all the questions we looked at. We found the molecular formula was C10H13N5O4. We then calculated the molecular weight is 267 grams per mole. There are 7 carbons with hydrogens, 3 without, 6 carbons with 4 sigma bonds, 4 carbons with 3 sigma bonds and 1 pi bond, 5 nitrogens that are different, 4 oxygens that are different, 5 double bonds, 2 rings, 13 lone pairs. And as a result of the trigonal planar, tetrahedral, those geometries, the molecule is 3-dimensional. So getting back to that quote by the Nobel laureate Feynman, we know a little bit more about AZT other than the name now. We've observed it, we've asked questions. The thing we need to dig a little bit deeper into, though, is this question in green. How do we actually know what the exact structure of AZT is? I mean, that is it. But, you know, as you advance in your college courses, this is a 200-level course, they're sort of ranked maybe according to difficulty or specialty. You get up to 300 or 400, things do increase in difficulty. So it's a fact, that's the structure. But I want you to imagine if you did not know that structure. That's what we're going to spend the rest of today's lecture looking at. How do we figure out what is the structure if we only had this white powder available to us, this substance? How can we go from that to that structure? You get a question over here?
How do you figure out on the molecular geometry of that
So with regards to the shapes, molecular geometries, when we get back to looking at carbon and how it bonds from the atomic orbitals to the molecular orbitals, we'll review those shapes. So remember Vesper, the SEPR, we'll review that next week. So how do we go from an unknown substance, if you watch CSI or whatever, the unknown suspect, the unsub, how do we figure out what it is? And the way that we do it in organic chemistry is using spectroscopy, which is the interaction of light with matter. And light is not just the light coming from the ceilings. Light is a spectrum. There's radio waves on the low energy, and then there's like gamma rays on the high energy, right? So we only see in a little bit of that spectrum. We see the visible part. So you're used to microwaves. I'm sure you've probably lived in a dorm and some jerks burnt a bag of popcorn stinking up the hallway, right? So microwaves are light, but we're used to thinking of light as things you see. So we're going to look at how these different wavelengths of light interact with matter. And that's going to then inform us of the elements present and the bonds they're present in. So we talked about this on Monday, but can you think of other forms of imaging? What?
X-rays.
So X-rays. So again, an X-ray is it's on the light spectrum, so it's high energy. Yeah. So CT scans,
MRI.
MRIs, yeah. So NMR, yes, that's what we're going to talk about. So NMR is radio waves. X-rays are high energy, right? That's what stars throw off. If you've been to the dentist lately, I mean, I get my teeth X-rayed once a year. So they put the lead apron on you, and then the dental tech walks out of the room, right? And you hear like, eh. And so that's the X-ray going through your skull. And so what is it doing? It's hitting core electrons in like phosphorus and calcium in your teeth. And then those electrons come out, they hit the photographic plate, and that's what gives you the image. But like you smile, you see my teeth, right? So why do you need an X-ray? Like you need to see inside. And so that's what how do we see inside? What does the molecule look like? So other things like MRI, that's more like soft tissue, right? So I've had an MRI done on my back. You got to lay perfectly still for like 45 minutes. And so why use an MRI and not an X-ray? So X-ray again is for like bone, and MRI is for like soft tissue, like muscle and ligaments and things like that. So these are imaging techniques that we use to diagnose what a problem is. You never go to the doctor when you're healthy, right? So you only go when there's something wrong, and they have to figure out what is wrong. Obviously, this isn't, 1850. You don't want the doctor cutting your leg open with a rusty hacksaw to figure out if your bone is broken or not. So when we get into Module 2, we're going to talk about NMR, which is nuclear magnetic resonance. Don't be scared about the word nuclear. It's not like Homer Simpson working at the power plant. It's not like radioactive nuclear. We're looking at the nuclei, so carbon or hydrogen. So those are the elements we're going to focus on. And this is an NMR spectrum. You can think of it as a photograph. So look at this photograph. There's an axis. The x-axis is called the chemical shift. And so there's some numbers 0 to 200. And so this is carbon NMR. So this looks only at carbon. We know there's hydrogen, nitrogen, and oxygen, but the light frequency that's used in this experiment only detects carbon. So the thicker line here, that's called the baseline. This stuff is the solvent. So if we were to take this is a solid substance, we have to make a solution. So we dissolve it in solvent to make a solution. And then anything else that's popping up off the baseline is called a signal. If you're British, us Americans call it peak. I typically call it a peak. So it's a signal, it's a response from the instrument. So that is the carbon NMR of AZT. So ignoring the solvent, how many signals do you see? The resolution is a little bit bad. I'll give you that, but so there's 10. So how many carbons were in the molecular formula of AZT? So 10. So the connection is we can see, using this NMR experiment, those 10 carbons. That's how scientists figure it out. So the question was, how do we know if something's unique or not? So because we see all 10 signals, that means all 10 carbons are unique. Sometimes we'll look at a molecule that has maybe 6 carbons, but then we only see 3 signals. What does that mean? that means their symmetry, when you're looking on that path, some of those are the same. So from the molecular formula to the observed signals, they sort of coalesce into one, and you see less than the molecular formula indicates. So carbon NMR, I know it's a lot of information, it's complicated, but carbon NMR is, all you're doing is counting those signals. It's just a line. There's the baseline, it goes up, it comes down, and then it sort of moves along to the next signal. It's just a line. Life being what it is, hydrogen NMR is more complicated. The signals look different than the carbon signals do. And the reasons for that will be covered in Module 2, but you can tell right away that it just looks different, right? In the same way that an X-ray looks different from an MRI. It's telling you different information. The chemical shift, the x-axis, now runs from 0 to about 12. So we still have a baseline. We still have signals. There's solvent. There's a water signal. Let me see if I can even read this. Can you read that? What is the sum of the numbers written in purple? You have it on your screen. Can you read it on your screen? Huh? Heard someone say about 12. Did I? So I'll write them in red here. 1, 1, 1, 1, 1, 1, 2, 1, 1, 3. So what does that give us? So 13. And remember, we counted by looking at AZT, it had 13 hydrogens, right? So the proton NMR tells you the total number of hydrogens. So I'll use the term to conceptually talk about this. I'll say ratio, or the spectroscopic term is called integration. So I've highlighted one of the signals in yellow there with a 3. Then you have this choice A, B, C, or D. What set of hydrogen atoms do you think that signal is assigned to? So D as in dog is the correct answer. Why is that? Because that's a CH3 group. So the signals are telling you the attached hydrogen. So that's why we went through that exercise of figuring out what's a CH3, what's a CH2, what's a CH. Obviously, in the proton NMR, you're not going to see like carbons that have no hydrogens, because there's none on there. That's not indicated in this data. So what you've done so far is, again, if you've taken that, you made the sample, you got this, you can say, okay, I know that there is a CH3 group somewhere in that molecule. The rest of the signals we can start to assign, and again, that's for a future module. But now the next question is, we've added these numbers up, They added the 13. Now what I want you to do is just count the signals themselves. How many signals do you see in this spectrum? So I think we have to cross out. I think we're not. Oh, sorry. So the ones with the purple numbers underneath. So count those. Yeah, I think 10's the response, 10's the answer. So what is the point of this? What are we trying to figure out? The carbon NMR showed 10 signals, there's 10 carbons. This is only showing 10 signals, but there's 13 hydrogens. So the reason those numbers are different is because, as we saw in the prior question, that one signal integrates to 3. So 3 of those hydrogens are in one signal. So the total number of signals that you see in a proton NMR is not going to be the total number in the molecular formula. So again, there's two different things we're talking about. So again, the numbers in purple here, that's the ratio. That must equal the total hydrogen count. The number of signals does not have to equal the total hydrogen count. And so what does that tell us about the hydrogens of the CH3 group? At a local level, those hydrogens are all the same. Because they're all the same, they occur as one signal. We won't talk too much about this type of spectrum in this class, but what I wanted to show it to you, it's a two-dimensional spectrum. There's the hydrogen NMR, there's the carbon NMR. And so what we do as organic chemists with this type of spectrum is we said that that signal was the CH3 group right there, right? So this is giving us the hydrogen information. And then what we see here are some blue and red blobs. If we draw a line with a ruler from there, we hit that red blob, right? Then if you go from that red blob on the horizontal axis, you hit that carbon atom. And so what this type of spectroscopy is showing us is we now know that these 3 hydrogens are attached to that carbon. And that's sort of a starting point that we can move along and figure out now what is bonded to this carbon. And so that's what this type of spectroscopy tells us. And eventually we paint a picture of what that molecule is. So here are those lines doing that process that show you how the hydrogen signals move over to the carbon signals. And at this point, does anyone play Sudoku? So I try to do a Sudoku a week just to keep my mind sharp. There's strategies you use in Sudoku, right? About eliminating responses based on moving right, left, up, and down. It's the same logic for this. I mean, it's like the exact same. And eventually you get to a point where it can only be that structure. And so just wrapping up here in the last couple minutes. So again, a molecule is a discrete collection of elements bonded together in a specific pattern. There's rules to the bonding patterns, CNOF, 4, 3, 2, 1. That comes from the periodic table, which comes from the electron configurations. The functional groups are identified through spectroscopy. We'll look at another form of spectroscopy called IR, so that's infrared Infra means before. Infrared tells us about, it informs us of the elements, but more about bonds. What type of bonds? Is it a single bond? Is it a double bond? Is it a triple bond? NMR is going to tell you number of carbons, number of hydrogens, and mass spectrometry tells you the mass of the molecule. And our last slide here, this is really what you're going to focus on the rest of for Module 1 before Exam 1, is learning the functional group names. So if you want to make note cards, that sort of thing, to learn these names, let me just walk you through it here in the last 2 minutes. So the methyl group, CH3, it falls in the family of functional groups called an alkane. This carbonyl group here that was bonded to the nitrogen and carbon, that's called an amide. This other carbonyl group, it's different. It's called a urea. The carbon bonded to the nitrogen and the oxygen is called an aminal, not animal. We have another alkane. So see the word alkane? But that alkane is a methylene group because it's CH2. The collection of 3 nitrogens together is called an azide. The carbon with the OH group is called an alcohol. The oxygen in the ring is called an ether. And then the carbon-carbon double bond is called an alkene. So there's alkanes with an A, there's alkenes with an E. Then if it's a triple bond, it's called an alkyne. So again, when I use those words, you really need to start picturing what those specific functional group patterns are. So we're about out of time, but again, your second quiz will open in 30 seconds. You have 24 hours to do that.